this 4-3, it still is a little bit, it should be a little bit unsatisfactory because the title tells you there's some major assumptions going on, or some major requirements for this process to work. A homogeneous linear equation with constant coefficients, right? There's a lot of requirements there. The next section after this is going to deal with what if that's not true? What if you have like non-constant coefficients or stuff like that? Or is it the next section or the one after that? Oh yeah, 4-6. So this one, the main idea was if I have something like this here, homogeneous, linear, with constant coefficients. A, B, C are just not functions of x, just constants. What was the form of the answer? What form would the answer take on? That's where we basically started. It's got to be some function who's related to its own first and second derivative.
cy, c1, y plus c.
But the specific form,
y equals e to the mx.
e to the mx. So it's got to be some kind of exponential, which actually leads to, in the complex case, we'll see how it leads to cosines and sines. So if we assume the answer looks like this, or one solution, right? And then we throw that bad boy in, this is where it really quickly becomes that a pure polynomial, which is looking at how degree and order are related in a way, in some cases. So of course, what's y prime? What's y double prime? Each one you get another. So what would y triple prime be? No way, okay. So I mean you can do higher and higher. It just becomes higher degree polynomials that you have to factor. Oh shit. So one thing I want to go over today is synthetic division, because it is a factorer's best friend. Just to make up a word, factorer. I like it. So if you plug this stuff in, you'll get am squared plus bm plus c times e to the mx, and I can divide by it because it can't be 0. So that assumption of an answer, which totally makes sense, because it's got to kind of be like terms with its own derivatives. And the only functions that we know are e. That's the one that definitely does it. Cosine and sine, not perfectly at all. But e is definitely going to do it. And then you just solve this. And once you get your M1 and M2, we looked at 2 cases so far, right? Then you just tell me that's the answer. Now, of course, if you get repeated root, we talked about, and I think I went through an example of where it comes from. We did it the long way, but now if you get a repeated root, so for example, if we had what you got, Jeff? What do you call that when we write this? We don't always do this work. We just go straight to here, but this is called the what? The word I had trouble with?
Auxiliary.
Yeah, auxiliary. All right. So what would the auxiliary equation be here? And the factors as? So you get repeated roots of 4. And just, you got to remember, this is in the background. This is always in the background. This is where things came from. So once you get the answers, you just plug those in. But this is only one kind of answer, repeated root. So I know that one answer is e to the 4x. And we figured out last time what the other answer is going to be. We actually did it the long-ass way, and then we went, holy shit, why would we do that every time? It's the same idea. Yeah, so it's going to be, the other answer would be x, e to the 4x.
Will it always be x e to the 4x?
Well, think about it. Try to go the next step. If this was a cubic, and it was, m minus 4 cubed equals 0, the next one would probably be
X squared.
That's great. And today we'll actually see them more directly. And again, I really desperately, you gotta go back to why this works. If we did it where if we knew one answer, we used reduction of order to get the other answer, and we realized no matter what the hell number is here, who gives a shit? The same thing would happen. So now we can make this a general rule. In one of the next sections, we're going to actually see this come popping out of some, well, we'll see, of some work we do. Let's try to say it right now. Yeah?
Sorry, I was trying to keep up writing. Where'd you get the x from y2, the x e to the 4x?
So again, last time we said we didn't know this. We knew this, so then we can use reduction of order, which is what we did, and we came up with that answer. Like I just said, right? If you know this is true, what's the whole thing with reduction of order? This is section 4.2.
So
You assume, okay, all right, maybe it's a good idea to do this again.
Assume one to get the.
Yeah, with reduction of order, you have an answer already for a second degree, for example, and you assume that y equals some u of x times that y1. All right, and then so that's what we did. Last time we got that answer. There was no other answer because it was a stupid repeated root. Stupid repeated root. So we went through all the work of reduction of order, and we got time to this. And then we got smart. We said, what if that would have been 5? It would have been all the same work. What if it would have been a -2? It would have been all the same work. So no matter what you get here, if it's a repeated root, it's going to be x times that one.
And we can only assume that if it's in that form, right? That
Yeah, it's got everything I'm talking about right now. It has to be constant coefficients, linear, homogeneous. You know,
So they won't work if it's
exactly.
something.
But you start to realize, you start with a lot of restrictions and you figure out what happens under those restrictions. And then you start lifting restrictions and seeing, how can I adjust it? How can I, it's sort of related to something called perturbation theory, where you get an answer and then you say, no, it's not quite the right answer, I need to change it a little bit. And how do you change it based on things? So it's, that kind of thing happens a lot in mathematics. So that's why it's okay to study something where there's a lot of restrictions and your part of your brain goes, not every equation is going to meet these freaking restrictions. Well, okay, we start here, and then we're going to adjust as we go. What if this restriction wasn't true? Oh shit, what would we do? Yeah.
Could we use that reduction of order? So we're talking about second orders, right? With reduction of order, we're talking about only second order.
It could be used for higher order stuff.
Can't you just keep reducing and then just keep replacing like a W, a Z?
Yeah, but think about it. If you had a third order thing, you would need to know
2 of the solutions.
fourth order. You have to know 3. So at some point, it becomes a little bit fantastic to believe that somehow you know 6 solutions to a 7th order thing, and you need to use reduction order. It's like, whatever you did, you just didn't finish it or something, you know. Do you see what I'm saying? But this idea of reduction of order is used to prove things like this, for example. So sometimes it's easy to think, well, what good is that by itself? I have to be able to get that damn answer it needs. But that process is used to prove other things or to fill in missing gaps, stuff like that. That happens a lot in mathematics too. Okay. Is everybody decent with this here so far? A little review of what we've done so far. Now, of course, if it's not a repeated root, then if I would have gotten m equals 4 and m equals 5, then it would have been e to the 4x, e to the 5x. And then what's the general solution here? C1, e to the 4x, C2, x, e to the 4x. Bam. Now, real quick, from another standpoint, why does it make sense that this might be an answer? Because what do you use on that to take derivatives? You have to use product rule, which allows for a piece of that product to be like terms with itself. I mean, you guys start to see what I'm saying? That's going to become important later today. That idea of how to look at it that way. This makes sense because it involves product rule, and then parts of that product rule are like terms with itself. When we start to get to the point where that's not 0 anymore, we're getting more and more into that pretty soon, where that's not 0. Right? Okay. Okay, so let's see. Those are the two cases we talked about. That repeated one and the one where it's not repeated. That's the best because then you got the answers. You're done. Fantastic. So the last case is if I get complex solutions from this. And I really, well, let's see. I was going to redo all the work the book does, and I'm like, why would I do all that shit? It's in the freaking book. Page 133. The only neat thing, really, to remember is the shirt I wear every now and again. You guys remember this one? Or you guys know this? You've taken 280. I would hope to God your teacher did something like this with you. What? Does anybody remember e to the I theta? How to rewrite that? I like the honesty. I love it. Good.
It's cosine theta, I sine.
Cosine theta plus
I sine theta.
I sine theta. And this is proven using Taylor polynomials, Taylor series, right? You write the Taylor series for this, and I don't know if you guys remember. Well, all right, I'll let you guys look at it. Well, I'm hoping you've gone through this already. I'm not going to go through this whole proof again with you. But basically what you do is you use the Taylor series to write this. You collect all your real terms. That becomes the Taylor series for this. You collect all your imaginary terms. That becomes the Taylor series for this. So this is a true identity. This is true using Taylor series, Taylor polynomials to fill in all those things. It does become true. It's very anti-obvious and very, but it's related to this idea. I don't know if anybody's watched. Do you remember if I left that link up for the further exploration of complex numbers? I love it. No, again, be honest, you real quick. What happens when you multiply something by -1? That's right. It goes through a 180-degree turn. Right? So there has to be ways to turn different than 180 degrees. And that's the idea of I. I is half of -1 in a way, right? Half multiplicatively. So that's actually, that would be a half turn. What's I times 1? Well, you turn halfway, and you get I. And what's I times I? So you turn and you turn 90 degrees and then 90 degrees. I times I? Negative frickin' 1. And then you multiply by I again. So you turn another 90 degrees. Negative frickin' I. And then you turn one more time. So this e to the I theta is another way of representing those terms. E to the I pi is -1 because it's a term. What's pi in terms of degrees? 180. So e to the I pi is a rotation of 180, which means that's -1 plus 1 is frickin' 0. That's all I'm going to say about that because that actually is something that should happen in 280. 280. That's where the 280 teacher should be. Oh, I'm so excited! I can finally show them this shit. So if they didn't show it to you, slap them. Because that should be one of the things I look for. Whenever I teach 280, I'm like, oh, sweet, I can show them this shit. Yes. Right, and you guys are all mostly like, Taylor series. Oh, they suck. They're freaking awesome. All right. Sorry. So this, when I get complex solutions, so just to look at the first bit of it, if I had this and I got complex solutions, I got m equals alpha plus beta I, plus or minus beta I. Just to use the same symbols they use in the book. They like these little alphas and betas. Now, when complex solutions happen, they show up in conjugate pairs, right? Like it. So this would mean that the answer would be remember e to the mx. So I get e to the alpha plus beta I x, and e to the alpha minus beta I x. So then I can split this up at e to the alpha, e to the beta I x, and then I can bring this thing in. You guys start to see how this would work? If I broke this up as e to the alpha x, e to the beta I x, e to the bix. And this would be e to the alpha x, e to the negative beta, negative bix. Do you guys see that? Is that cool? You guys okay with that? Sometimes people aren't. They forget that when you add exponents, that must mean you were multiplying like bases. Right? We've used this a lot with constants happening all the time. Right? This piece, I can rewrite using this. Is that cool? I can rewrite this piece using this. I can reorganize shit. I can define my constants however I want to. And I end up with the solution to case 3. Complex roots. After I do all that reorganization, I do end up with what's down here. You can kind of see this already happening. I get y equals e to the alpha x, c1 cosine beta x, plus c2 sine beta x. So it's using this, which is a really neat thing. If you're interested at all in mathematics, you should be interested in this. I know a lot of you guys are like, I am an engineer. I want applications. What is this shit? Too damn bad. You're in math class. Engineer's hell. All right. So let's do a quick example of this kind of thing, case 3, and then I'm going to give you 4 problems to do on your own. Let's see. Ooh, that's gross. I like that one a lot. It's not too bad, actually. Okay, that'll work out nice, actually. So try to write the auxiliary equation down. Try to, hopefully you quickly give up on factoring. Some of you guys say, I give up on factoring before the problem started. Poor little beta. Feel bad for this beta. Alright, I mean, let's see. What's the Ox equation? M squared minus m plus 7m. Get those down there. Equals 0. So you got m equals. Yeah. 1 plus or minus square root of 1 minus
28.
28 divided by 2. So you get square root of negative 27. 9 times 3. Yeah, okay, I like it. So you get 1 plus or minus root 27I, which is 3I root 3. And then you just identify what's alpha, which beta. What's alpha here? 1/2. What's beta? Alpha is the real part. Beta is the imaginary part, coefficient. Careful, no i's in there. So 3 rad 3 over 2. So alpha plus beta I. So beta is the coefficient of I. All right, let me stop here for a second. Everything we've done so far in that problem, starting here down, is like math 90, right? It is. Okay. I want to make sure everybody understands that. It's all math 90 shit, right? Now we got to step back and say, all right, really, to be honest, you just know this form, you just got to plug stuff in. So alpha is 1/2, so your y equals e to the 1/2 x times c1 cosine of 3 rad 3 over 2x plus c2 sine 3 rad 3 over 2x. You just have to remember this form for this case. And then you just plug stuff in, yeah.
Does the I next to the sign disappear into C2 since it's a constant?
What you do is you choose your constants correctly. If you follow the book's derivation, they pretty much, there's a couple steps they sort of skip, but they talk about them. If you choose your C's carefully, you can get rid of that I. Yep. It doesn't really disappear. Although it looks like it does.
Just becomes part of the constant, right?
Yeah. Oh, I see. So yeah, it gets sucked in. So what we're looking at. Okay. I mean, that's that case. And you need to memorize that form. Because I love the kid that told me, when I get out to my real job, I can just have all these sheets, formula sheets and shit with me. I'm like, well, that's then. That ain't now. Cry me some tears and learn the damn form. I like it. You guys aren't like that. I like you guys. You guys, we're like they were just quiet. All right, let me give you a few nuts and bolts problems to try that go through the 3 cases. And you got this sheet. You can use this sheet to help you. Right? So everybody got that sheet?
No.
Okay. So here, we put these up here. All right, so try these out. Let's see. Ooh, you're gonna like this one. You're gonna like it. It's hard to do these without writing